Now if you take a Zener diode, it has a breakdown voltage Vz, which you don't know what it is, and you want to measure the breakdown voltage. You want to determine experimentally what that voltage is. You have to understand what you're doing, and what you're doing is, if you take a current versus voltage graph here, there's your current, there's your voltage. This is the anode, that's a cathode. But if you take this in the normal direction, if you increase the voltage in forward bias, what you'll get is it'll get to a point where it'll do that. And that point there is your normal diode drop. Call that 0.7 volts. Okay? That's in the forward direction. In the reverse direction, as you apply more voltage to there and there in reverse bias, what you'll get is you'll get zero current flowing, and then suddenly it'll hit the breakdown voltage and it'll start allowing current to flow, and then it'll do that. So what happens is, when you get to this point, you've reached your Vz. Well, actually you've reached negative Vz. And if you measure that, if you can measure that point, you know what your voltage rating is for that Zener. So it'll be a 9 volt Zener, it'll be a 5 volt Zener, it'll be a 24 volt Zener, whatever, all right? So to set this up, you really need to create a condition where you can measure the voltage across the Zener and control the voltage that you can apply in reverse bias. And to do that, you simply put a current limiting resistor on here, and you apply a plus voltage on there, and you connect that to ground, and you measure that there. So if you measure the voltage at the Zener and you apply the right voltage with the right resistor and the right diode, you get your Zener voltage on here. The way to set this up is to choose a resistor that won't do any damage and that will give you enough current through the diode to give you a reasonably accurate breakdown voltage. And the right current is neither here nor there. The maximum current is easy. You know, if you've got the formula P equals IV. If you've got the power rating, let's call that a 3 watt diode, and if you've got unknown current, and if you happen to have a 15 volt diode, then you know that your current equals 3 divided by 15, which equals 1/5, 0.2 amps. That's your I max. So that means that if you have a 15 volt Zener and you pass 200 milliamps through it, you'll reach your 3 watts. If you exceed the 200 milliamps, you're going to overheat your Zener diode and you're going to blow it up. Okay? So 200 milliamps is quite a bit of current. I mean, this could be a 5 watt Zener, it could be a 300 milliwatt Zener. Okay, so what you need to do is create a situation like this, depending on what voltage you're going to use, where the current limiting resistor resists or reduces the current to a reasonable amount. Okay, now in the example that I want to show you, I've got a 24 volt supply, and I want, let's say, a maximum of 10 milliamps. And if I don't know what that Zener voltage is, I'm going to call it 0. I'm going to call that 0, as if it was a short. And it could well be shorted, okay? So when I apply voltage to this, I don't want puffs of smoke to fly up. So the maximum current I want through there is 10 milliamps. I have this now to calculate. R equals 24 minus, if that is 0, 24 volts divided by 10 milliamps, so 24 divided by 0.01, which is equals to 2.4K. Let me call that a 2.2K, 2.2K ohm resistor. So let me set that up and I'll show you how this voltage becomes visible when you measure it under these conditions, okay? So here's my setup. I have a variable supply coming in here from my power supply. I have the ground of that supply connected to the anode of the Zener diode. I don't know what that value is. I haven't looked. I really don't know what that value is. I have my 2.2K resistor over here. I have my multimeter connected across the Zener diode. Now what I'm going to do is I'm going to start increasing the voltage on the supply, and we'll see what happens. At the moment there's a bit of residual voltage on there, and our Zener diode has stayed at 9. So that tells us that that thing there, and I'm increasing the supply even more, it's up to 18 volts. That's up to 9.1. So that tells us that our supply is in fact, rather our Zener diode is a 9.1 volt Zener, or a 9 volt Zener. The precision is not absolute here. Now I'm going to increase this to 24 volts. The supply voltage, the top here now is 24 volts, and we're getting 9.13. My guess is this would probably be a 9.1 volt Zener. I believe 9.1 volts is in fact one of the values that you get as standard. And it's all very well. There we go. It's a simple system. You can set it up and you can find out what your Zener voltages are. But it's a pain in the ass to do this if you've got a whole number of Zeners lying around. Some of them might not even be Zener diodes. So to set this up every time you want to measure the value of a diode is just too much. So there are ways we can make this simpler by building a dedicated Zener voltage tester. And again, there are many ways of doing this, and I've seen quite a few on the web and how they go about it. But I've decided to look at my way of doing it, which is to create a method of measuring Zener voltages with variable currents, test currents. You can adjust the test currents, but where you won't damage the Zener diode, and also that you don't have to use a whole lot of connections to set it up. I want this to be as self-standing and as simple as possible, and I think that that is what I have achieved. Let me show you. You would have a constant current source made up of an LM317 voltage regulator IC. If you look at the data sheet for the LM317, you have in, you have out, and you have reference. And the way you can turn this into a constant current source is by putting a resistor here and connecting the reference to that. And the way this works, your current, your constant current, I, equals 1.25 divided by R. This is R over here. This is your I over here. And the reason it's 1.25 is that the reference voltage internally used to determine the output voltage of this, when you use this as an adjustable positive voltage regulator, it's got a reference of 1.25, and you create a resistor network around that to give you the output voltage you desire. When you use it like this, that's exactly what happens. You're basically eliminating the other resistors, and you're creating a constant current source. When you connect this to a load, that becomes a constant current source. Now, what is the load in this case? Well, the load in this case is going to be my Zener diode under test. And that side goes to the negative of the supply, or the ground, 0 volts. That's my supply over here. So, if I create that there and I put my Zener across there, and it's always going to give me, let's call this 10 milliamps, then I can simply measure across here with a voltmeter, and that'll give me the Zener breakdown voltage at 10 milliamps. Now, various ways of doing this. I could put in two sockets or pins where I could simply connect my multimeter onto the ends of that. I can do it in various ways. What I've decided to do is actually, I've decided to use one of these things that I find very, very useful and very, very cheap. And that is the modules these guys are using or selling on the net. It's this thing over here. This is a 0 to 30 volt module. And what it does is you connect your black one to ground, the red one to your positive supply. So that would be a supply. Let's call that the supply over here. You've got to be careful not to exceed it. I think the maximum is 30 volt supply. And this goes to the point you want to read. And what you're going to read is the voltage across there. Now, what will happen is, when there's no diode over there, what you're reading is really the voltage coming in here, your supply voltage. Call it 30 volts. The minute you put a diode across here, a Zener diode across here, or even a forward bias diode, you could do that as well. If you do a forward bias diode, this thing will break down at 0.7 volts, so you'll get a reading of 0.7 volts over there, and you'll know that you either have a Zener forward biased or you have a normal silicon diode on there. But if you put it in reverse and the 10 milliamps flows through it, it'll give you the breakdown voltage, and it'll give you a very handy, very simple, very small, and very cheap little voltmeter. That's the first module that I'm using. Okay, so what does this mess show us? It shows us a ground from the supply. The positive supply goes to the in pin of the LM317. It's the pin 3, this is in reverse. Between pin 1 and 2, which is 1 being the reference pin and 2 being the output, so that is pin 2, that is pin 1, and that is pin 3. We have a resistor on here, and at the moment I've got a 220 ohm resistor. 220 ohm resistor, which if we work this out, it works out approximately not 10 milliamps, but about 5 milliamps. Okay, so just happened to put that in because I'd used this in a previous circuit. Now, what we have then is the out, that pin out there is this yellow wire. The measure tag, the blue one, goes to the out there as well, so it's going to measure the voltage effectively across the Zener, and then the Zener is going to get connected to ground. So if I put this on ground, I've got basically the same circuit, and which way around is this? We'll just watch what happens when I power this up. 6-ish volts. Now I have a slight drop here because there's a drop across the linear regulator. So instead of 6 volts, I'm measuring 5.4. But we know that Zener is 9 volts. We happen to know that Zener is about 9 volts. So if I increase this, it's going up. I'm increasing the supply voltage. Same way I did before. It's now on about 8, and we've got about a 0.6 across the LM317. If I keep going up, it's now at 9. Keep going up, and it's stopping, and I'm at 10, and I'm at 11, and I'm at 12. You see what happens? We've got exactly the same situation, and I'm going to put all this all the way up to 24 volts. It's at 24 volts, and my voltage there is 9.1. So I know that is a 9.1 volt Zener. Basically, I've replaced the voltmeter. In the case of the circuit here, this voltmeter, instead of being the multimeter, is now this internal, very cheap, very simple digital voltmeter. The resistor calculation is done away with by using the LM317 constant current source. At the moment, it is set for 5 milliamps, but I can change that resistor to make it whatever I want. Now, the only other thing is, what do I need to make this self-standing? Well, there are two ways of doing this. One of them would be to actually use the positive and negative supply coming from the power supply. So I could have a situation where I actually plug in a variable power supply or a power supply. Bear in mind that I don't need to vary the voltage anymore. I can set it at 24 volts, and I can then measure any Zener I put on here that is less than 24 volts. Let's see, this one, I have no idea what this is. Let's put it on here and see. That's a 4.7. I can't read this, can I? Ah, bloody hell, that's the whole point. This is far too small for me to read properly. Here's another one. 7.8. Now, what I want to do is make this as compact as possible into something like this, where I'll have two little clips and I can just connect the Zener on there, whether they're croc clips or whether they sort of button points where I can actually touch the Zener to. I'm not sure yet. The power supply is a question I haven't answered yet. I don't want to mess around with a variable supply. So I do have a possibility, and I will show you. I've been playing around with this already. And what I'm considering doing is actually using a 18650 cell. You can either buy them like this, but you can also salvage them from portable laptop supplies. Then using one of these modules, again another module, this thing actually is a USB charger module for that, and all it does is it provides me with a socket for the actual battery for the cell, and it provides me with the charging circuit using micro USB. So if I put the cell in there and I want to charge it, I can charge it through that. Then I have the voltage coming out here, which is anywhere from 3.8 or whatever to 4.2 volts. And then I can boost it with another module. This is module time, man. This module boosts anything from 3 to 30 volts, and it boosts it up to 35, 40 volts, something like that. So I can actually boost my 4.2 volts up to, say, 30 volts and use this as my supply in a fixed situation where all these things, everything will fit inside that box. And that's what I'm considering doing, and I just need to see whether everything will fit. It will work. I need to see what other modifications I want to make. This would be the power on and off so that it wouldn't drain battery unnecessarily. This would also possibly even use a push button one, push to make, release to break, so that you only push it when you want to test it, because the whole testing scene is quite instantaneous. There are no heat considerations because this is used for very short periods of time. When the battery gets down there, I can just plug this in and charge it again. The other thing I could possibly do, and I think I will do, is have a switch where I can switch in that resistor or switch in other resistors in parallel with that. So this is set for 5. So if I put another 220 ohm resistor, it'll give me 10. If I put in something else, I just got to work it out, it'll give me about 15 or 20 milliamps. So I can actually switch what range of test currents I want to use. But those are all things I'm just trying to decide on now. I'll give it some thought and see where we go. So let's just draw the schematic of exactly what it is that we're trying to achieve here. We're going to be using a battery, an 18650 battery, and we want this thing to be chargeable. So we have a charger there. The next step, we've got 3.7 to 4.2 volts DC. The next step is we're going to take the same voltage and we're going to input it into the booster. That booster module, and the output, which happens to be a common ground, is going to be, let's call it 30 volts. So we've got 3.7 to 4.2 going in, 30 volts coming out. That's our power supply. Then we're going to take the voltage regulator, the LM317, we're going to do that. In order to get 10 milliamps, we're going to put in here a 120 ohm resistor. So that gives us approximately 10 milliamps. Then we're going to take that, and those are the two connections, whether they be crocodile clips or just metal studs on the outside of the box. That's where our device under test will go. Then we need to add the meter. That meter is connected to ground. It's connected to that point there, which is the same as that one, and it's connected to plus, call that 3.7, that's connected to plus 3.7. So what we have is the battery, which is chargeable via USB. It charges the battery. It goes into the booster. The booster boosts it up to what we want, and in this case I'm going to use 30 volts. I'll tell you why in a second. It goes into our linear regulator set up as a constant current source, providing 10 milliamps, and it goes into the device under test, and that there, when it measures that voltage, that'll tell us what the Zener breakdown voltage is. Now, why some of these limitations? Okay, the battery I'm using because it's convenient. These things last a very long time. These charger modules are very, very cheap and they're easy to use. You can actually get a charger module that has a booster incorporated, but the best module you can get is the one you've got on hand. It explains a bit of the philosophy here. The booster can go up to, I believe it's about 40 volts, but I'm putting up to 30 for the simple reason that my meter here can measure 0 to 30. I don't want more than 30 volts at this point, otherwise I exceed the limits of the meter. And that's the meter module that I have. So I can measure, if I put in 30 volts there, I get about 29.4 volts. I can measure Zener diodes up to 29.4. And that's what I'm going to build now. Just when you think you've got the schematic completed, there's always something that comes up that you haven't thought about, and therefore this whole thing gets scribbled on. But just for clarity, here's the final schematic. Just a quick explanation. This here is the 18650 cell. This is the USB charge controller for that cell that comes in one module with the holder for the 18650 cell. Very easy to get hold of. Then it goes through, you have a momentary switch, which is the power switch, because you only do need this for a second or however long you want to test your device, and we don't want this thing draining the battery. So you push that in and your voltage goes into a DC to DC booster. It's boosting 3.7 to 4.2 volts from the cell to about 25-30 volts, whatever you want, as long as it's less than 40 volts because of that LM317. This DC booster is also quite easily available, and any one really can be used. The LM317 then acts as a constant current source through a selector switch. It's a 3-position switch. The center position just leaves the 220 ohm resistor in line with the output, which goes to the device. The first position leaves 220 ohms in line. That gives us just over 5 milliamps. I think it's 5.45 milliamps. If we select the switch up, we put a 270 ohm resistor in parallel with that, which gives us about 120 ohms, which makes the constant current 10 milliamps. And if we turn the switch down, it brings 82 ohms in parallel with 220 ohms, which gives us a result of about 60 ohms, so that's 20 milliamps. And that's the current that you select to go through your device. Then we have the meter module, which again is very easy to get, and the one I have now is a 0 to 30 volts. I've ordered 0 to 100 volts. They're very, very cheap and very, very accessible. And that's connected to the positive voltage there, coming from the battery as well. Also after the switch, so you don't waste battery. It's connected to ground. Those are the two power lines. And then the sense line, which is the detection line, goes to the same point there on the device. So when you have current flowing through it, your reading in there in volts will be the Zener voltage. And that's basically it. Our schematic is complete. One more thing, just one more thing. This connection was left out. This wiring point from the reference pin of the voltage regulator IC to the output was not in the schematic that we've been talking about just now. So this is the only change that needs making. Make a note of that because otherwise it will not work. All right. And I hope you, if you haven't, I hope you see the first video in the series, which is actually the build of this device. I wanted to make it simpler for people who don't want to go through all this theory and all this schematic drawing and development, which can be quite boring if you don't enjoy this. But I wanted to make it easier for them to just go ahead and build it if they like. So, hope you enjoyed that, and see you soon.